Hello, my name is Fedintsev and I am Chief Scientific Officer at Radical Life Extension Group. And we are an early stage startup and we are aiming to radically extend lifespan of humans. And next slide please. And so I always like to cite one of the smartest human beings on earth, Nobel Prize winner, physicist Richard Feynman. And he said that there is nothing in biology yet found that indicates the inevitability of death. This suggests to me that it is not at all inevitable and that is only a matter of time before biologists discover what is causing us the trouble. And I totally agree with this brilliant scientist. And well, basically, there is no physical law that limits lifespan of biological organisms. And we know that some species live hundreds of years, like Greenland shark or bowhead whale, like with a lifespan of over 200 years. And so we want to live exactly like hundreds of years. Why not? It's in principle it's possible. And so our goal is to radically extend lifespan next place, and we define radical life extensions as at least twofold increase in life expectancy. Not like 20 years, not like 30 years, like at least twice. So why aim for something lower than that? And ultimate goal is of course achieving the famously proposed longevity escape velocity, when every year we add more to the life expectancy than 1 year, right? So, and then there are a lot of going on in the field, right? So we have discovered several genes that extend lifespan drastically in animal models, right? But then there is a question: so are these discoveries applicable to us? Like, are these most promising like gene therapies applicable to adult human beings? And then this next slide I have, yeah, are we close to radical life extension? So next slide please. And in mice, it seems that we are pretty close to radical, like at least our definition of radical life extension. So for instance, here is the growth hormone receptor knockout mice, which lived like roughly 50% longer than their wild counterparts. 50% life extension is like it's a pretty good life extension, right? So in human beings, if we're like boldly translated to humans, that's like over 40 years of additional healthy life. But then, so why shouldn't we try it right away, like this intervention? Why shouldn't we knock out like growth hormone? But it turns out that it's not like as straightforward as it seems to be. So because, for instance, next slide please, scientists discovered that the growth hormone treatment in the early childhood, because these animals with knockout of growth hormone, these are transgenic animals, and they have growth hormone signaling deficiency from the very beginning of life. And if we treat these animals with growth hormone in a very early childhood, then we get a pretty big decrease in lifespan, which means that the vast majority of effects that this mutation produces happens in very early childhood, and thus growth hormone deficiency cannot really extend lifespan of an adult in a similar fashion. So and this another study confirms this. So next slide please. So when growth hormone receptor was knocked out in adult animals, so there were virtually no increase in life expectancy of males, and some increase in maximum longevity of female mice, but not statistically significant. So we see exactly this. So some of the most promising genetic interventions cannot be applied to adult organisms. And unfortunately, this is not only for growth hormone. Next slide, please. Another most promising intervention is overexpression of so-called FGF21. This youth hormone is pretty famous. It extended lifespan of mice by up to 40%, which is a remarkable achievement, right? But then, yeah, and it's interesting that it's a soluble factor, so you don't need to modify all the cell, like every cell in the body, to achieve like effects of the rejuvenation. So you can inject this copy of this gene into some cells of the body that will produce the FGF21 in a soluble form, and it will rejuvenate all the organisms. Good idea, like they're very nice. And I know that George Church, for instance, included this FGF21 into his cocktail, like genetic cocktail. And it is believed that FGF21 increases insulin sensitivity, reduces like fat mass, and do have a bunch of good stuff to the human organism. But then, to the mice organism, of course. And then, but then I found a very, very interesting detail. So next slide, please. The thing is, like, very suspicious thing, that actually FGF21 levels increase with aging in both humans and rodents. It means, and if we think logically, then it means that the overexpression of FGF21 most likely has the most effect in the very early stages of life, when naturally FGF21 is low. And moreover, in fact, it shares the similar mechanism of increased longevity with growth hormone receptor, because next slide, it actually inhibits the growth hormone signaling. So basically, FGF21 gene therapy may not be very efficient for us adult human beings, and that's why we actually don't have anything that works like can give us like 30 to 40% or even more right away. Next slide, please. Yeah, but then do we have something that actually works like for us, like even potentially? So for adult human beings. And yes, we may have a drug or several drugs that extended lifespan of adult mice, right? So mice that starting not from the early childhood. And for instance, one of these drugs is Canagliflozin. It's an anti-diabetic drug which extended lifespan of mice by about like 14%. So it's pretty good. But the remarkable thing is the mechanism by which the Canagliflozin extend lifespan of these mice. Next slide, please. This drug happens to reduce blood glucose spikes, and it was shown again on the mice model that these blood glucose spikes. There were two groups of mice. One group of mice was on a regular diet. Another group of mice received glucose, like sugar. And the average level of blood sugar were the same in two groups, but the treatment group had these blood glucose spikes. And after a while, maybe in a couple of months, this second group developed atherosclerotic lesions in their arteries, and they were pretty significant. So we can see that the difference is huge. It means that that these blood glucose spikes might be the underlying cause of atherosclerosis, because we can in human, next slide please, in human beings we know that high blood glucose, these glucose peaks, impairs endothelial function in blood vessels and increase oxidative stress, which Michael, for instance, mentioned that oxidation of LDL particles makes them atherogenic, right? So we have several studies, and moreover, these blood glucose spikes, next slide please, they are associated with risk of dementia, and you can see that that people with with frequent blood glucose spikes have like 50% increased risk of developing dementia, while people with the lowest frequency of blood glucose spikes have like 50% like less risk of developing dementia with time. And then, but then there's a question. So, for instance, I'm a healthy man. I have a normal glucose, both fasting glucose and even normal glucose after 1 hour after like basically any meals, right? I also have a normal glycated hemoglobin, and other markers are okay. But then I decided to wear a continuous blood glucose monitor for a couple of weeks and see whether I develop blood glucose spikes. And I thought that it's not the case for me, right? But then I was super surprised when I found that actually these blood glucose spikes occur constantly after meal, like every day, several times in a day. I have blood glucose like of 8.6, even more than 9. They quickly disappear, but then they still damage my arteries and promote atherosclerosis. And so I decided to like test different medicine and see how it influences blood glucose spikes. And next slide, please. Yes, and I took similar medication to Canagliflozin, the extended lifespan of mice. It is called dapagliflozin, and it's a very interesting. It has a very interesting mechanism of action. So evolutionary, we were our bodies evolved in a way to preserve glucose because it is a very valuable resource, right? So, and thus our body uptakes. Kidneys uptakes the glucose from urine and return it to the blood. And these drugs prevent this process. And so we can throw away excessive glucose and avoid spikes, and also reduce the average amount of glucose circulating in blood. So these drugs work very well for diabetics, but it also seems that they reduce spikes in healthy persons, right? Previous slide still. But then still some meals still causing blood spikes, even when I take this dapagliflozin. But then I tried another drug called acarbose, which basically prevents some of the oligosaccharides and polysaccharides to be absorbed by intestines. So it breaks, it inhibits some enzymes that are responsible for that. And spikes disappeared completely. Blood glucose is nice and steady, low, and this I think definitely plays a role in increasing my chances to reach longevity escape velocity. But then, next slide. Unsurprisingly, acarbose also extends lifespan, and it does it by like 15%. But what's more interesting, next slide please, what's more interesting, is like how many years we can get from eliminate, like theoretically, what the upper limit, what we can get from eliminating blood spikes. And it was calculated by some reputable scientists that eliminating all cardiovascular diseases in the United States of America will result in additional 70 years to life expectancy. I mentioned that that blood glucose spikes also are associated with dementia onset and also with diabetes. All in all, if we just boldly combine these values, we'll still get less than 10 years of additional life expectancy. So it's pretty good, but it's not that many years, right? So it's not radical life expectancy still. What can we do about that? So how can we go beyond that? And what if we, for instance, combine some drugs? And next slide, please. Next. And then, indeed, so some combinations may work. For instance, very well-known geroprotector rapamycin combined with aforementioned acarbose, they extended lifespan by a remarkable 37%, both sexes in mice. And this is very remarkable because 37% in mice, it is a result that was shown only by caloric restriction, like before that, caloric restriction or some genetic interventions. And these were already adult mice, right? So this is I think this is a very promising study. And we can test this combination right now. So nothing prevents us from doing this. And this is quite a recent paper. It was published in October this year. So pretty good, but still 37%. It's not 100%. It's not radical longevity. And I doubt that if we combine more and more drugs and maybe other interventions, I highly doubt that we can achieve radical life expectancy, so twofold or more increase in lifespan. Why I think so? Because majority of drugs, majority of gene interventions, they influence, they target mostly cells and molecular mechanisms, molecular pathways that occur inside cells. But as it was previously mentioned, our organisms, it's not just a bunch of cells residing in air, right? It's a majority actually of matter in our body is extracellular matrix, which is composed of long-living molecules. These long-living molecules naturally and inevitably get damaged, right, over time because of various things. Mechanical damage, chemical damage, glucose, products of lipid peroxidation. So they damage these molecules, and this damage alters structure of these molecules, alters their mechanical properties, and these in turn influence cells, and they stop function properly. So there is a dysregulation because cells are adapted to work properly in a certain environment. And so I have proposed several ideas which are reflected in the review that you see. I proposed that this is a 10th hallmark of aging. Yeah, and this is one of the study that favors this hypothesis that shows that old stem cells, mesenchymal stem cells, seeded on younger matrix gets rejuvenated, but young cells seeded on old extracellular matrix, they basically gain phenotype of old cells, and also all the functional parameters go down. then next thing. So I believe, and I propose the hypothesis that cross-linked ECM induces cellular senescence, and so that cellular senescence is a mechanism that prevents fibrosis. And like cross-linked H8 ECM looks very, very similar to a fibrotic as ECM, and these senescent cells try to counteract this. But since there is no fibrosis, their efforts are futile. Okay, and then another thing, that how extracellular matrix may impair cognitive function. This is on the picture. You can see the mechanism of synapse formation. So to form a synapse, special cells like microglia, they clear the matrix to create a space for axon and dendrite, right, to meet actually and form a synapse. And when the matrix is cross-linked, it becomes very resistant to enzymes that different cells produce, and it cannot be cleared as easily as it was in childhood. And this purely mechanical, mechanical thing can explain the decreased synaptic plasticity that happens with advancing age, right? So, but what our company, what our team is focusing on is again elastin. Elastin, you've already seen, right? So this is a molecule that is responsible for elasticity of different tissues, of our skin, of our blood vessels, heart, lungs. And it is the remarkable thing about elastin is that it is deposited only in infancy. There is a short window of the high elastin, tropoelastin, and other elastogenesis gene expression, and after that, the expression of these genes falls down, remains on a very, very steady low level. That's it's basically zero expression. And this elastin is basically deposited in infancy. It stays all the life with you, until you're dead. So the half-life of elastin is estimated to be 100 years. And it gets damaged by pulsatile stress, for instance, this stress and strain cycles, by oxidation products and so on and so forth. And you can clearly see on the picture, so there are notable differences in structure and in appearance of ECM, of elastin. And it has the consequences. Elastin loses its mechanical properties, and it leads and not cross-links, but actually damaged elastin leads to loss of elasticity of our skin and loss of elastic properties of our arteries. And this is why it is important. So next slide. Yeah, so and some scientists estimate that the maximum longevity of human beings is limited by elastin, because roughly by 110 years, elastin is completely degraded, and our arteries lose elastic properties completely. Why is it important? So next slide. So this is important because of so-called Blindspots effect. This is a German word. I probably pronounce it incorrectly, but the idea is that heart when it beats, when it contracts, it creates a pulse of really powerful blood flow, right? And elastic aorta, it dampens it, right? So And it ensures that the blood flow is slow and steady. Yeah. And if there is no elastic recoil in the aorta, the capillaries are damaged, like every time heart beats. And this is happening in multiple organs and tissues. And this is what limits our lifespan, right? And thus our team. Next slide, please. Next. Next.
While you're about, I'll get people in, but don't be discouraged. Continue.
Next slide. Yes. Yeah. We are developing a vector that contains all the genes that are necessary for elastogenesis. Because there is a problem not only to express like proper elastin and some other genes, but also to ensure that elastin assembles in a proper mesh, right? In a proper structure. And by carefully studying the literature and tons of kind of natural multi-element data sets, we figured out a way how to like coordinate this process. And so this is something that we are actively working on this year. Thank you.
All right.